Hello, my name is Dr. Michael Okreke. Welcome to my channel on getting started with modeling. This particular video is aimed at RVE modeling, the modeling of unidirectional composites. So I'm going to show you how you can set up within a finite element scheme a setup for unidirectional composite, but we are focusing on just a representative volume element version of this UD composites. We're not looking at it at the laminate scale, we're only looking at it at the unidirectional level. If this is the kind of content that you're interested in, please do subscribe to this channel so that when videos like this are made, you'll be the first to see it. I'll also encourage you to please subscribe to my channel so that the knowledge about these videos can continue to spread to others. So let's go to the PowerPoint slide so you can see what I'd like to talk about. So first and foremost, this is an image that's taken from this publication, by Amy Wiggins and her colleagues. And basically what you find here is a micrograph of a unidirectional composite, which essentially consists of fibers that are laid up in this way and other fibers are laid up in the other way. So this is like a bidirectional composite. So it got two layers of fibers, one in the other direction and the other in the other direction. So if you then build this within a CAD model, you probably get something that looks like this. Admittedly, the fiber arrangement here is quite odd, and real composite do not necessarily look like this, but this gives us an idea of what we're trying to basically do. So you can I like you to note the dimension. Basically this scale is 50 microns, so we're going to be modeling at double that scale at about 100 microns. And so this is the RVE. This would be the typical kind of problem we're going to do. We're not going to model it at the laminate scale where you average the behavior of this laminate, but rather we're going to model it at a representative volume element. So what do I mean by that? So if we then look at the next slide, so basically I can isolate a cubic RVE, a cubic representative volume element of just one of those bundles of fibers. So what you end up getting is probably something that looks like this. So you've got a cubic RVE with the fibers running in that direction. If you decompose that into two components, you end up with a fiber and a matrix component. So we've got a fiber and a matrix component, and what you want to do is to represent them explicitly within a finite element scheme, apply boundary conditions onto them, and then get the behavior of the composite using this, which is an RVE. So this is suitable enough to give you the whole stress strain behavior of this composite, and we're going to go through the whole range of responses to make sure that we're able to capture this information properly. So then just look at a little bit more about the details. So this is our RV that we're going to model. It's three-dimensional system. Some people do model this as a 2D system where you're only interested in what's happening on this face. But we're going to do it in a holistic manner by doing a 3D system. Our RV will be cubic, so the length and the width and the height will all be 100 microns. And then the materials that we are going to be using for this modeling would be a glass fiber reinforced plastic called GFRP, glass fiber reinforced plastic. The fiber will be made of A-glass with a Young's modulus specified of 73 gigapascal, and the matrix will be polypropylene. The Young modulus of the matrix will be 1.308 gigapascal. The matrix will allow it to plastically deform, so it's got a yield stress. The volume fraction will be 35%, and each of these fibers will have a diameter of 20 microns. Now, the case studies that we're going to use, we're going to try and assess a wide range of loading for this RVE modeling. So the first one is tensile deformation along the z-axis, which basically means this. So we're looking at deformation along the z-axis being the fiber axis. So obviously the behavior is going to be dominated by the fiber. The second case is where you start doing a transverse to the fiber loading. So in this case we are moving in the zx direction, so you've got the x direction. And then I'll try and do a compression testing on this material and also the transverse direction where the behavior of the matrix will dominate the response. And then we'll try and do a shear deformation on the XY plane, so the XY plane being that plane. And then of course we'll try and do a third case, which is the YZ plane, which is the plane where the fiber is dominating the response. So this is what we are going to be doing in this. So 5 case studies to be studied within this RVE modeling, and try and learn something about the behavior of the composite based on all that. Now In terms of building this RVE, how many fibers do you really think will fit within a window to capture this volume fraction that we're looking for? So basically, the way to think about this is we've got a fiber. This is a typical RVE with a diameter of fiber specified. We don't know how many fibers will fit into this window. We know the length and width. We choose a length and a certain width. Like I said at the beginning, we're going to modeling at 100 microns. So the length and the width will be 100, 100, as well as the depth of the RV 100. Now, the term volume fraction basically means the number of fiber n times the volume of each fiber, and the fibers are cylindrical, so it will be pi d squared h, divided by obviously the volume of the matrix, the whole composites, the volume of the composite. So if you take the ratio of the number of fibers times the volume of each fiber divided by the overall volume, that gives you volume fraction. So that means here we can make n the subject of a formula, which means we have a relationship that looks like this. So now for this our case where we are dealing with a 35% volume fraction unidirectional composite of diameter of fiber 20, the length and width and the height all being 10. So clearly the h will cancel out in this case. So if we then apply that, so it comes up for this case, we're looking at probably around 11 fibers, at about 11 fibers to make this problem possible. So this is what we're going to be modeling. Now, I generated randomly the fiber locations using a Monte Carlo algorithm, just a randomization algorithm to locate the locations, to find the locations of the fibers. So each fiber will have an XY coordinate positions. And the other thing that I've done here is that where you have a fiber, a part of it is cut out. In order for periodicity to be maintained, I replicate that fiber at that corner. So you can see here it's replicated there to make it complete so that the volume fraction will be retained. If you've got a fiber, the other bits gets replicated. I mean, this is typically what you do within computational modeling, just to make sure that you don't end up having, reduced volume fraction. It's a bit artificial, but it does work. So again, if you see here, you've got a fiber there, cut off being replicated there, as well as that. So it's a slightly more complicated scenario, but we're going to work with that. So I've given here the positions of each of these fibers, from the numerical scheme that I used to generate them. So we're going to be creating the model based on these positions, and then as we move on. The other thing to think about is how do we apply our boundary conditions. So for our Uniaxial X, Y, or Z loading, so I'm going to make the back. So basically this is a kind of loading arrangement that I'm going to be using for my uniaxial case. So I'll put roller support at the back end and roller support at the base end, and then pull the model in this direction so that you can then contract this way and stretch out that way. In the shear cases, so I will constrain in X and Y direction the back face and constrain the front face. So this is a bit like simple shear. Apply the loading in this direction, then you get a shear deformation that looks like that. So that's the overview of what the theory behind what we're trying to do. So now let's get over to ABAQUS in order to get this modeling started so that you can see how we're going to go about this. Okay, here we are in ABAQUS. So we're going to first start by creating, so if we just look very closely, so if you go here, so I'm going to start by creating the first model. So this I'm going to call my matrix. Okay, and matrix we know is 100 by 100, so let's make this 4. So the matrix will be created using this. So at the base here, I'm going to put the coordinate 0, 0, 100, 100. So that gives us the directions, the dimensions of the matrix. Okay, and then done. Okay, so that has to be as deep as 100. So this gives us a cubical picture of the matrix, so this is fine. Now we'll start dealing with the fiber. So we start with the fiber. Okay, so I'll just create it there. So what I'm going to do is I'm going to give myself a bit of a leeway in terms of how I'm going to create this fiber. So I'll provide a framework. I mean, this is typically what I would do. So I'll create the boundary within which I'm going to create the fiber. So that's fine. Now I'm going to create a fiber. I place my origin here. The coordinate position will be 10 and 0. So I've got a fiber created effectively there. So what I'm going to do with this fiber is I'm going to translate this fiber into different positions on this structure to make sure that I'm able to, to get it forming what we're interested in. Okay, so we'll be referring to this table, and this table, basically the coordinate positions here, we'll start with the coordinate position of the first fiber being at 35 and 51, 35 on the X and 51 on the Y. So we're going to translate this fiber from where it is. So if I click on this translate button, create a copy, select the fiber starting at the origin to 35 and 51. So if I show you 35 and 51, so we put the coordinate there. Now we see the fiber has been translated to the location that we want. Okay, so the next fiber is going to be translated to 40 and 8. So click the translate button again, copy, select this from 0 position to 40 and 8 in the second case. So that's the second fiber. So the third fiber would be at 1824. Okay, click on that, create a copy, select, start from 0 to 1824. Okay, so we've got the three fibers. So we're going to do this so that we can populate this, and then we'll come back and do it. Okay, so here we are. We've done all the positioning of the fibers and everything is in their right place. So we then need to extrude, but before we do that, we'll click on delete. So this mask that we used for reference, I'm pressing down shift, you can select it multiple, delete that. So that goes away, and then we can extrude. We can click done again. So we want this to also be 100 microns. So we've got all the fibers in their location. We need to create instances. So under assembly, select both of them. So instantly you begin to see it's looking like a unidirectional composite. Clearly there are things on the side that we don't want, so we want to be able to trim this. So what we're going to do is we select the two instances and click on the merge cut. So we're now going to call this UD composite. Okay, return all the intersections, merge, suppress, return all the intersection. We select everything and click done. So what this will do is it will suppress the previous instances, create a new instance called UD composite. So under the part module, it will also create a new entry called the UD composite that we're working with. Okay, so now based on this UD composite, we're going to have to trim. So we're going to use this create cut extrude option. So select the plane to extrude cut. So we select, okay, I want to extrude, and then select the edge. I want this edge. Okay, so I'm going to use a way of extrude cutting this. I click on the rectangle button, start on one corner of the matrix to the other corner. So we've got that, and build a bigger one around it. So this would give you a way of cutting, trimming off what's on the boundary. Right click, cancel, and click done, and then click through all. So it slices through everything, giving you a clear RVE that looks the right kind of RVE that we're interested in. Okay, so then the next thing we need to do is to do the material. So I'll click on material. So this I'm going to call my E-glass. So we're working with E-glass. It's going to have an elastic property of 73 e to power 9 and a Poisson ratio of 0.3. So we're going to do the polypropylene. So the polypropylene will have elastic properties of 1.308 e to power 9 and 0.4 Poisson ratio, and the plasticity of this will be 40 e to power 6 and 0. Just a simple elastoplastic model should be sufficient. So we have this as our case. Okay, then we create the sections. So our fiber section would be selected, so E-glass fiber, and then our matrix section, which is polypropylene, would be polypropylene. So we've got all that in place. Then everything is in place. Then we'll go back and do a section assignment. So double click on here. So I'll select anywhere in the matrix, done. So I'll assign that to my matrix. Okay, Now I'd select everything, select anywhere in the matrix. So to deselect the matrix, I don't want to create any set. So this becomes my fiber. Okay, so I'll change to material module to make sure that I have everything looking the way it's supposed to be. So this looks all right. So the fibers in place, the matrix in place, and we've got our UD composite the way it's supposed to be. Okay, so we can go ahead and do some meshing. So to create a mesh, so on our meshing, so it's predicting 5, so maybe we could try something like 2. Okay, so just to get a finely meshed model, so I'll select everything here, and I'm going to use a sweep medial transition, minimize mesh transition argument. So we'll check and see what kind of result we are going to obtain. All right, so it's a hexahedral element meshed the right way, and we got something that okay could be acceptable. So I'm happy with this. You can further refine the model, but this looks all right for this kind of simulation. Okay, so then the next thing, we've done section assignments, we've done profile assembly. What about the analysis step? So analysis step is going to be a loading step. Static general is accepted, so we'll select that. Now boundary conditions, so we need to think about how we're going to constrain this structure and apply our load, and also because we're interested in getting stress and strain history from this data. So the first thing I'm going to do is I'm going to create a reference point. So let's click the query button, point and node, and find the location of this corner. Okay, so that corner is basically has a value of 0, 0, 100. So I'm going to create a reference point a little bit away from it. So under tools, reference point. So instead of 0, 0, 100, so maybe let's do 150. Okay, so that creates a reference point here. And we're going to use the reference point to control everything that's going on in the model. Go to the assembly module, under features, set. So I'm going to call it my RP set, reference point set, control. So we've got this set called the reference point set. Now I try and do some other set, continue. So I'm going to select everything on the Z face. Okay, so we're going to create nodal sets for different things going on in the model. So under the path module, so if I double click on set, so I'm going to call this Z front. Okay, continue. So you select, basically you need to painstakingly select all the fibers in the front face, making sure that you don't miss out anything. Okay, so call that the Z front. So we've got that. So we'll do the same at the back. So so Z, so double click on set and Z back. So continue. So we'll rotate this and then basically do the same at the back in the Z direction. So select all that, making sure you don't miss out anything. I'm pressing down shift so that I can do the multiple selection as you go through. So this is really important because you don't want to apply the load and certain parts are not being seen. So this is fine. So we'll go back to our symmetric view. So look at other faces. So the Y top, so the Y face top, so I select all that. Okay, and then I'll do the same at the underside. So Y bottom, so we continue that. So we're going to use this as a way to control what we're trying to do. Okay, now so we go back to our symmetric view. So we've got the Y top and the Y bottom. So then the last bit is X front, which will be, again I'm pressing down shift while I do this multiple selection, and then we'll do the same. Say okay, X back, continue. So rotate it to the back, and then basically you do that. Okay, so that's also all done. So if you go back to the symmetric view and then you switch this to a set, so it could show you the different set that we've created. or with different colors, so which basically tells you that you've selected the sets properly. So this is all done and we're happy with that. So now the next thing we're going to do is think about our boundary conditions, but because we have different cases we want to work, so I'm going to rename this ways and call it case 1. Okay, so if we do case 1, no, so this, okay, no, so that's not what I want. So case 1 is still there. Okay, so let's work with case 1. So we've got everything. So what we're going to do with case 1, again, the assembly module are fine, so I'm going to constrain the back and fix the front. And so I'm going to apply the boundary condition. We're pulling it in the X direction, so double click here. So this will be fixed back, okay, fixed Z back. It will be an initial boundary condition. I'm going to use displacement module. So this is where the set comes in. So our X back, Z back comes in. So we're using the Z back and we're constraining it only in the Z direction. So we don't want it to move in the Z direction. We'll like it to contract as well. Yeah, so let's look at the Z direction, only constrained there. And then the other thing we need to apply also fixed, or instead of fixed, let's call it roller in the Y base bottom. Okay, so we're using the Y bottom, so we highlight that. Okay, that's fine. So that will now be in the Y direction. So if you think about what's happening here, we'll fix the base here, we'll fix the back here, so we're going to pull the front. The system will be free to contract in this direction and will also be free to contract in that direction. I mean, technically we could also look at the other direction and see whether we can fix it in another direction. Maybe we'll do that. So if we do this, so what I'm going to do here is the X back roller. Okay, because we are doing a 3D problem, so our X back highlighted, so we are going to fix it only in the X direction. Okay, so we have a system like that, then we can pull in one direction to get the right response that we're looking for. Now, to get our displacement, we're going to use a constraint, an existing constraint to do this. So what we're going to do is we'll create a constraint. So I'm going to call it my constraint. So this constraint will be based on an equation. So Z constraint, let's call it Z constraint. Continue. So it would have to be 1 here, the nodal set that we're working with. So if we expand this so that we can see clearly what we're doing. So the nodal set we're working with will be the X front, obviously, and a degree of freedom 3, -1, and we're linking it to the reference point, and 3 is the direction. So basically we specified a star equation here linking this point to that point, so that if we then go ahead and say, okay, we're going to apply a displacement load, so displace Z, okay, in the loading direction displacement, so we can attach it to this reference node. Okay, and we're moving it in Z direction. The system was 100 meters, so a strain 100 micron, a strain of 10% will mean a displacement of 10. So you can see what has happened here. So we apply the load here, and this load will be translated to what's happening in there. Now what we're going to do is we are going to create a history output to be able to monitor this. So our stress, so call it stress strain history, or reaction point history data. So let's call it that. So reference point history data, and we're going to extract all the reaction forces on that reference point. Okay, so all the reaction forces, X, Y, Z reaction forces, and all the displacement. So X, Y, Z. So we're looking at the X, Y, Z displacement of those faces, and because we're going to use it. So this is a little bit like doing an experiment where you get a force displacement profile. So we're using the information on this point to extract all that. So let's just say, okay, case 1 tensile Z. So we'll run that. Okay, So we can then look at the simulation and say, okay, submit. So this should then run and give us some results. So I'll just delete this model 1, and then I can duplicate this case, copy, and then this will be case 2. So what do we want to do with case 2? Okay, so our case 2 is a tensor deformation transverse to the fiber axis along the x-axis. So we're basically pulling in the x-axis. The fiber axis will be there, so we are doing a transverse deformation. So so if you look at the case 2 now, everything will remain the same. Where the differences will lie will be in the boundary conditions, where we position the boundary conditions. So we're going to pull in the x direction here. So if we're pulling in the x direction, so the x back, the fixed back roller would be okay, so we're not going to move that. The bottom will still be okay, we're not going to move that. So the other bit will still be okay, fine. So everything we have here essentially will be fine. So this is fine, that is fine. So the only place we need to pull is the front end. So our displace, so what I'm going to do is the displace Z, I'm going to copy that and call it displace Y, and I'm going to suppress the Z option. Okay, now with the Y option, so instead of it being in the 3 direction, we want it in the Y direction, so this will be 10. So think about it. So we've got the loading here in the 3 direction, but we also need to change the constraint, because our constraint was constraint Z, so I renamed that and call it a Z constraint, an X constraint, but it's going to move from this face to the face of interest. So instead of the Z front, we are going to do the X front. Instead of being in the degree of freedom 3, will be degree of freedom 1, because this is X. So what has happened is that we've got the loading here translated to what's happening there. Okay, so that gives us the right simulation for that. So we can double click there and say, okay, case 2, tens X. Okay, so we're doing a tensor simulation in the X direction. All right, so this is fine. We can submit that to run as well. So we submit it to run, and while that is happening, so let's go back and use case 3. So I'm going to create a copy of case 3, case 2, but that becomes my number 3. Now what is case 3 going to look like? So let's just study that. Okay, so case 3 will look like this. So it's a compression in the Y direction. So we're compressing in the Y direction, transverse to the fiber as well. So let's model that. So in the Y direction, okay, so I'm going to change the loading. So this will be displaced in the Y as well, but it's going to be negative, but not in the Y in one direction. No, so it will be in the 2 direction, and it will be a negative load minus. So that means I'm pushing down. Okay, so the fixed Z will be fine, the other bits will be fine, the X back will be fine. So the only thing that we need to change is what's happening at the top here. So that means our constraint, so the constraint equation that we'll work with will now be, if I rename that, I'm going to call it a Y constraint. So Y constraint. All right, so what would the Y constraint be? Okay, so I'm going to move it from X front to X top. Okay, and then degrees of freedom will be 2. So basically I'm pushing here, and then I'm tying it kinematic constraints to that bit, and then that should really work. So we can then, while case 3 is selected, do case 3. So compression Y, comp Y. Okay, so we'll submit that model as well. So we'll be running, and then we can be creating the other cases. So we've got X, Y, Z. So the next thing is that we're going to think about the shear case, and any of them should work. So maybe we could use the third one. So I'm going to call this case 4, case IV, number 4, and it will be basically a shear deformation. And so the shear case says we're doing a shear case on the XY plane, and then the final one will be on the YZ plane. So working with the XY plane first, and then finally on the YZ plane. So let's go ahead and model. So the XY plane will be this plane. So basically this plane on the X axis in the Y direction. So we are pulling in the Y direction and X is free. So our loading, our displacement will still be displaced in the Y direction, okay? But I'm going to make it a positive case because I want the shear to go up. So we're shearing in the Y direction, but we're applying our load on this face. So there are a few things that will have to go. So basically on the back end, on the back face here, what are we going to get on the back face? So we're going to get on this back face a deformation where we're fixing it securely in all directions. So what we have here is the X back. So the X back, I'm going to rename that to X back fixed instead of, because it's no more a relaxed support. And it wouldn't just be fixed in the X direction, it will fix probably in all three directions, X, Y, Z. The front end here, X front, so we don't have X front here. So I'm going to create an extra case and call it X front pinned. So it's not really securely fixed. So we are going to attach it to the X front. But this X front will have X and Y reinforcements. So it's fixed in that, but then it's free to move in the two directions. So it's free to move in the two directions. So that's what we've got here. And then obviously our displacement load will be linked to that face as well. And how are we going to do that? So clearly we need to cancel out this particular one at the back, at the bottom. So X, Z, Y bottom. So I'm going to suppress that. So I'll suppress that. So it's not free to do anything in that face. The back one also needs to go, which will be fixed back. I'm going to suppress that. So thinking about the boundary condition we've used, so we fixed at the back and we are rolling at the front, keeping the system the way it's going. Then we think about the constraint. So this my constraint, I'm going to change it to an XY constraint. XY constraint to reflect the shear. So you open that up. So this is very interesting now. So because we want to constrain the X front, okay, so X front is where we're applying our load and it's moving in the two directions. So this is why it's a shear in the X, Y, X being the face and 2 being the direction. Okay, so we've basically linked that to that. And then with that, okay, so we can then create a simulation. So this will be case IV shear XY. Okay, shear XY. Continue. Okay, and then we'll submit that to run. So it will run as well, generate the result that we're interested in, and then we'll carry on. So the final thing we need to do is, while the job is running, so we'll go back and find the other scenarios. Okay, so copy this model. So this will be case V. So case V would obviously be the shear in the Y direction. So basically we're sharing the front face. So we're sharing the front face. So let's look at what our boundary condition is. So we'll still go in the Y direction, shear YZ. So so the face is Z, and then we're moving in the Y direction. So this is fine. So we're still using displacement in the Y direction, but obviously our constraint will be different. So we'll rename that and call that YZ constraint, and then we'll adjust that accordingly. So if you open that, it will be on the Z front. So because we're applying our load on the Z front, but we are displacing in the third direction, the third axis. Sorry. So we're still displacing in the two axes. So we end up with YZ, Z being the face, okay, like YZ or ZY, however you want to call it. Now the displaced Y would have to be linked differently. Displaced Y would have to be in the Y direction as well. So it's a positive Y value, so which is fine. So we've got this face linked to that face. Okay, so this is good. So we've got this face linked to that face in the right way. Now we need to sort out the boundary conditions. So clearly, if we're displacing this face, the back has to be securely fixed. So we are going to have to resume the fixed back. So I resume that, the fixed back, but I'm going to constrain it in all possible directions because the back has to be securely fixed. Roller at the bottom. So the next bit is that we have to put the one at the front here, so the fixed. So the Z front would have to have a load. So we'll create that. So Z front pinned. Okay, so let's work with that. So displacement. So we're going to link it to the Z front. So it will be constrained in the 1 and 3rd axis because the 2 axis is clearly not acceptable. It's gonna be the degree of freedom through which you move upwards. So applying the load moving up on this face, that is fixed. So the other bit we can suppress. So Z back is fine. So front we suppress that, and Z pinned. Okay, this is fine. The back. Okay, so this which other one? So we've got this is fine. So this setback we don't want, so we're going to suppress that. All right, so let's just study what we have done. So basically on this beam, on this structure, the back end is securely fixed. So let's make sure this is what we want. Fixed securely at the back in every possible direction. Okay, so that's what we want. So we want securely fixed at the back. The Z front is fixed so that degree 2 is the only direction that you're free to move, and this is what we're going to use. And our displacement in the Y direction is there and it's linked to a Y constraint, so everything is fine. So we then go ahead here and create a job for this case, call it case 5, Shear YZ or Shear XZ, ZY, whichever way. They're basically the same. So you submit this. So we've submitted all the models and they are running. We're going to then wait for them to generate the result, and we can study the result and get the stress strain plot for them as best as we can. So this is a plan. Okay, all the models have finished running. It took a bit of a while for them to run, and that's mainly because initially I had quite a very finely meshed model. If you remember, if I open to the UD composites, the meshing was set at a seed side of a global seed side of 2, so I've changed all that to a seed side of 5. So that meant it could actually mesh, it could run quicker and mesh quicker. So it took each simulation to probably, using a desktop PC like this, it took about 3 or 4 minutes for each model to run. So it shouldn't take that long. It should take about 50 minutes for everything to run, really. But because my mesh size was very high, so it took a longer time. So we're going to visualize some of the results. So case 1. So if you look at the results on case 1, okay, so this is kind of where we are pulling in the fiber direction. So if I animate that, so you can see what's happening. So we're pulling in the fiber direction, and the model is obviously the whole response is being dominated by the fiber. So it's a tensile pull in the fiber direction. So what about the transverse direction? So case 2 results. So this is where we are pulling in this direction. So you can see what's happening. So again, we're pulling in this direction, and it shows some interesting case. So if we look at the plastic strain, which is always the best measure of what's happening, so it shows you basically that there's a bit of plastic deformation in the metric side and the fiber remain undeformed. But then you get different kind of responses depending on the way you're looking at it. So this typical behavior that you see with a UD composite, as the fibers are in their position and things are moving around them to show you that kind of response. Okay, so what about the other direction? So let's look at the third case, which is compression in the Y direction. So we're looking at compression in the Y direction. So again, it makes sense to look at the plastic strain. So what we're basically doing is that we're pushing on the top in the Y direction. So you're pushing the model on the top. Obviously the formation looks a bit like when you're pulling on this other direction. Okay, and what about the shear cases? So there's case one, which is the in-plane shear. What would the in-plane shear look like? Okay, so you end up with a behavior, so you're shearing on that face and you're moving that up. It may be a good idea to exaggerate this shear slightly. So instead of 1.5, can we double that to about 3? Then it gives you a better estimate of what's happened. So if you look at the plastic strain, again, it gives you a story about where the plastic strains are being developed. I mean, you can notice that the fibers are being pulled around in this deformed state. So if you think about here, so the fibers stay in their place and the matrix is being pulled around it. And these are all very interesting. So there's a bit of shear distortion. If you look at the shear values in the 1-2 plane, so again it shows you where the shear is being dominant, the 1-3 plane and the 2-3 plane. So the best measure to see some distinct differences would be that, and then if you animate that, you could see how the model is adjusting under this shear loading. And then the final case would be where you look at the shear in the fiber direction. So basically we're shearing in the fiber direction and it shows really some interesting results. So if you animate that, so obviously the fiber is being pulled, the back is fixed and you're shearing about this fiber direction. Obviously the fiber properties will dominate significantly the behavior of the system, and you can see the kind of a kinking profile to how the fiber will look like and differential values on the fiber on those faces. So some interesting result that you get by studying what's happening on the fiber direction. So let's create multiple viewports, maybe 5 viewports for all of them. So again, I'm gonna tile, maybe I'm tiling them vertically, maybe to see what we are going to see. So from the first one here, you're going to get okay, let's just make it symmetric. So tile a 6th one, so and then tile horizontally. Okay, so the first one here is the case 1, the second one here is case 2, no, case 2, yeah, the third one here is case 3, the fourth one here is case 4, and the fifth one here is case 5, and we could also replicate and say just this case 5, it doesn't matter. Okay, the other thing I want to do is I want to link all the viewports. So link viewports, so get them into their different faces, and then okay, so what's case 5? Why is it not showing? Okay, right. Okay, so right, so let's just get it back into his face the way it should supposed to be, and then we can animate that. So it shows you different kind of responses that you're interested in seeing as the fibers are changing. So what about the plastic strain argument? You end up with different plastic strain values. Okay, so if we zoom closer just to have a better picture of what's happening, you could see different fiber response, different fiber behavior based on what we see here. So the fiber dominant response, the other directions are all in place, showing you different kind of responses that you would normally you will get. So these are all nice, interesting results that you will get based on the behavior of the system as a unidirectional composite. So What would really be interesting now that we found what they look visually is to get some kind of stress strain data from it. So what we're going to do is, okay, let's just maybe pick one case. So maybe let's try this case 3. Okay, so let's study this case 3. So we'll click on that point, click on this point, and then we'll look at the history variables. So what is case 3? Case 3 is you're pulling in you're applying a compressive load from the top. Okay, remember we're applying a compressive load from the top in the y direction. So that means if you open here, you're going to look for the reaction force in that direction and the displacement in that 2 direction, plot them. So you could see this is a reaction force and the displacement. Okay, and then unlink the viewport because it's generating it for all the cases, and that's not what we want. So we'll go there, history output, continue on the history output. So we are going to use the case 3 model. So you click there, history output, continue, select the reaction force in the 2 direction and displacement in 2 direction, because that's what we are looking at. We're looking at movement in the 2 direction. Plot them. So you see it gives you the reaction force and the displacement. So we click on that again and go to operate on this data. So basically we have to combine them. So we combine. So there's this combine button. So displacement against force. Okay, so you plot this expression and then you can see it gives you this data, force against displacement in compression, which is what we're doing. So we're going to then visualize this in Excel. So plug in tools, Excel utilities. So from ABAQUS to Excel for the current plot. So for this current plot, so we'll go there. So what this will do is that if you have Excel in your system, it will open it up. So if we enter here, so what you will have here will be displacement and reaction force F2 in the y-axis. So displacement in the y-axis as well. Okay, so the other thing we then want to is our strain and our stress. So it gives you a bit of a plot here which you can work with, if you like. So our strain will be equal to the displacement divided by the gauge section. Our gauge section is 100, and the force will be equal to the reaction force divided by the area, which is 100 by 100 for this cubic RVE that we are using. So you get that plot there. Okay, so we could then plot these two, insert column data, that. So you can see it gives us a plot of stress versus strain. Okay, maybe while you're still on the stress, maybe we could say, okay, 1 e to power minus 6 times that. So that will give me my stress in Pascal, okay, in megapascals. So basically this is megapascal. So that's the stress in megapascal. Then if we want to find the Young's modulus for this direction, so this will be equal to the slope. So obviously we want the slope in the elastic region. So elastic y values will be that, comma, and the elastic x values will be those, comma, close. So this gives you this value. So we could divide that by 1 e raised to the power 3. So that gives you gigapascal, Young's modulus. Now, yield strength or strength, you can call it yield. So this will be equal to the maximum, about that's typically maximum for elastoplastic system of the y value. I mean, obviously you can find other ways to use in getting this. Oh yeah, so this is so this is the so the absolute, because it's that, so the absolute values of that. Okay, so that gives us that. So this becomes megapascal. All right, so this gives us the values that we generate. So we've got a stress strain data for this y2 direction. and we've got also a plot, we've got the values. So this is kind of what you probably need to do for all cases of the examples that we've studied, and that will give you an idea. But we've just done it for compression in the y direction. It will be the same for tensile case as well as other cases. So that's all I wanted to show in this video. And if this is the kind of content that you like, please do subscribe to this channel and click on the notification button so that when contents like this are made, you'll be the first to see it. So I'll catch you on the next video. And if you have ideas about videos that you would like me to make, please include that in the comment section, and also use the timestamp associated with this video to run your way through this video, because it's clearly a long video, so that you can get insight into what I've done. Take care and catch you in the next video. Bye.